Okay, now Zoom is recording. Okay, sorry. Where do we think we should put it? Yep.
You could put it underneath A or on A.
Underneath A or on A. Yeah, those are two really great potential positions to put it. So we can either put it here, right, where it even tells us like, hey, you should potentially measure X from here, right? It's telling us we're gonna call this X. So that's probably a good direction for X to go. Or we can put it right down here. And either of those is perfectly valid. You need to be consistent throughout the problem, but I'll go ahead and tell you, I chose, for better or for worse, I chose to put it on the ground. And I said, this direction is X and this direction is Y. You can choose either, perfectly valid. Okay, so we did part one. And then part two is sometimes the hardest part of the problem. You need to take what's written in words in the problem and usually interpret it into the variables that we're used to working with in our equations. And that's what makes this step so great, is that it can sometimes jog our memory of what equations we're supposed to be using. Because we start to realize what variables are involved and we're like, oh, most of those variables are in that one equation. I wonder if I can use that. And more often than not, you can. Okay, so let's see. We know what might we know about maybe some like initial positions, initial velocities that we could write down that's given the problem, yeah?
The initial velocity is given by the square root of 2g.
Yes, absolutely. So the initial velocity is given in the problem. So we can say that like v0 is equal to v equals square root of 2gh, where h equals 2. So we can go ahead and even plug in something like this maybe. Now notice I didn't give that a vector sign. So is there anything we might already interpret about maybe the direction of that initial velocity? Yeah, you can tell that by the way it's given. But it's also just the nature of water coming out of an orifice, is it's going completely to the right, at least to begin with, before gravity hits it. Yep.
For h, why did you put 2?
Because 2 is given in the problem. H equals 2. Yep. Okay, so I'm going to interpret this as v0, the vector, is entirely in the I hat direction of whatever the heck this number is. Okay, so now I have interpreted what the problem has given me into the math that I'm going to need later. And then what else might I put down? Do I know anything about acceleration, maybe? How much is in the x direction? How much do we accelerate in the x direction for projectile motion? 0 I hat. And then what do we put in the y direction? 9. Positive 9.81 or negative? Negative 9.81 J. Very good. Okay, and that's actually acceleration always. So this is a function of time. And then there's one last piece of information we can drag out of this problem statement, and it's related to position at t equals 0, or the initial position. What is the initial position of our particle?
0 plus 1.5 J.
Beautiful. That's about all I can wring out of that problem statement. Okay. So I'm going to leave it there. Those are the two steps that you can basically do for every single problem you are ever do in this class. And so if you ever look and start to feel like you're overwhelmed, do those two steps first. Remind me y'all's 3 names. Is it Samuel? Samuel what?
One time.
What was that?
L-A-M-N-I-C. C as in cat, Z as in zebra, AK.
And then you guys?
Joseph, Moses,
Joseph,
Moses, Emma.
Got it.
And Omar.
Did I get it?
Yeah.
Thank you guys so much.
Honestly, I completely forgot about it, and then I woke up about 9:54. I was like, wait, oh shoot.
I'm impressed you got here that fast.
5 minutes late.
I'm not taking attendance for any official reason. I'm just interested in the analytics of who comes and how grades go.
I mean, sampling bias, to be fair. I know for me, I'm just not one to miss it. I just so happen to be.
I just want to let you know, I'm still really late.
Not a problem. No problem.
Image.
Yep. Come late, leave when you need to. You don't need to let me know. Had a thought. I was thinking it would be really nice for me to be able to immediately tell by looking at y'all, like whether or not you're stuck on the problem. Have you guys ever been to those, Brazilian steakhouses where you have the flip
Oh, yeah,
thing,
the
the green and red cards? I wonder if we did that and you had it like flip to green, it means you're still working on the problem, but then once you're like, all right, I can't do anymore, you flip it to red and then I can like hold the room and know when to start. That might be good. Oh, so it's like you get these cards. It's usually like a coaster. One side is green, one side is red. And whenever you have it on green, all these servers come by with like giant racks of meat and they cut you a piece. And then when you're ready to like eat and stop for a minute, you turn it to red so they stop bothering you, and then you eat and then you turn it back to green. It's amazing. I am bad in that I don't care about sig figs. I care more about decimal points, and I usually just say I'd like it to be correct within 2 decimal points. For that. tugging along mostly. Mike, are you done? Yep, question?
No, I'm just fine.
If you currently feel a little stuck, I want you to do exactly what you two are doing. Partner up with someone who looks less stuck and try to get over the stuck. Those of us joining on Zoom, feel free to ask questions anytime you like, okay?
Alrighty.
I did my inspiration on the position. Yeah, that's just the wife.
Yeah.
That's 9.81 times 2. Should be divided by 2. I don't think that changes the thing.
No. Would you? Let's confirm.
Okay, I'll give y'all 2 more minutes and then I'll start solving on the board.
I integrated from 135 to
Yes, you can.
R is like that.
You have the velocity. Your velocity is by the opposite. Yeah. Right side is by. And then you find R. So you can do that. R.
Just find it for food.
Right. Something noises? Yeah. Okay, I'm lost. What is it? Joseph. Okay. If you're in a groove, stay in that groove, but I'm gonna start putting a solution on the board. Let's see.
The final thing, like what is the,
It asked for find t and rx when ry is equal to 0. R of t, we should get as 6.264 t I hat plus minus 9.81 over 2 t squared plus 1.5 j hat. Okay.
I did it, so.
Alright, so now find t when ry equals 0, where everything on the I component is what we refer to as Rx, everything on the J component is what we refer to as Ry. So I need to set minus 9.81 over 2 t squared plus 1.5 equals to 0. Solve for t. You should get t equals plus or minus 0.553 seconds. But is it actually ever a negative time? No, so we just take the positive solution. Okay, so time is really only positive. So t equals 0.553 seconds. And then it says find the x position when this is the case. So now we need to take that t and plug it back into Rx. So Rx equals 6.264 times t. So 6.264 times 0.553 equals, what'd you get? 3.46 meters. Very good. Okay. Any questions on this one? It seems like we got to some stuck places, but then got past them, so that's perfect.
I did it. I did 2 integrations, one for the x components and one for the y components.
Yep.
Should I not do that?
I used to teach it that way. I used to do, I would break everything into separate scalar problems, a scalar problem for the x direction, a scalar problem for the y direction. There will be concepts later in this course where you don't want to do that. So for instance, when we're dealing with moments, we're gonna have to take cross products of vectors, and it's really, really best to leave thing as a vector. That's why I've stopped doing it that way. It's not invalid. It's just that I find it easier to stay organized in later problems if I just keep everything as vectors from start to finish. Any other questions?
I mean, I can read.
It's a matter of organization, which as the problems get longer, gets more and more important.
Yeah.
Okay, all right. Let's do our normal tangential coordinates problem. Also, just as like a kind of step higher level meta thinking, realize that problem, we just spent 30 minutes on it, on one problem. So the problems in this class, and we're still early on in the class, they take a long time, okay? Now, if we're doing an exam where we have an hour and 15 minutes to do 4 problems, we maybe can't spend a full 30 minutes on it. So that's why the practice of doing problems over and over and over again and getting efficient at solving problems is really, really important, which is why you're here. Exactly why you're here. All right, normal tangential coordinates. A race car C travels around a horizontal circular track. I'm actually on this one. I'm gonna highlight things that are standing out to me in the problem. Circular track that has a radius of 300 feet. If the car increases its speed at a constant rate of 7 meters per second squared, starting from rest, determine the time needed for it to reach an acceleration of 8 feet per second squared. The reason I'm highlighting these particular items is I'm basically going to go through each of these phrases and interpret it in terms of math. So on that second step that I said, after we draw a picture, where we interpret the problem in terms of math and write down our knowns and unknowns, these are the things that are gonna give us those expressions. Okay, so we have a picture, and in fact, they already did this for us. They already drew in the normal direction and the tangential direction. Okay, it might be a good exercise though to see if you could have done that yourself. So if this car was moving clockwise around the circle, would you have known that the tangential direction goes this way and the normal direction points into the center of the circle? Hopefully you did. Okay, so I'm gonna erase my scribbles. So we already have a coordinate system. We have a pretty good picture already. So I'm gonna say step 1, draw a picture, is already pretty much done. There's nothing I really want to add there. 2, interpret knowns and unknowns. So here's where I'm going to go through each of those highlighted phrases. So we're told specifically that this thing is a perfectly circular track, which means that there is a constant what about this path? Curvature, radius of curvature, right? When we're talking normal tangential coordinates, in fact, one good thing might be to go ahead and say, all right, I think I'm going to use normal tangential coordinates. In fact, they've already shown me on the picture that I'm using normal tangential coordinates. I'm going to go ahead and write down acceleration in normal and tangential coordinates just to remind myself what variables are involved here. The light bulb needs to be that what they are giving you here, when they tell you it's a circular track with a radius of 300 feet, is that they are telling you that rho is equal to 300 feet. All right, tell me about the next part. The next part says the car is increasing its speed at a constant rate of 7 feet per second squared. How do we write that in math? Okay. dv dt. Does this v have an arrow bar or no? No, because speed is a scalar. Very good. Speed is a scalar. Can I rewrite the way, like, is there a different way to write this expression? V dot, and that's what shows up in my equation here, right? Okay, so they're telling us that that is equal to 7. Very good. What is the next highlighted part? What does that tell me? Starting from rest?
No, sorry. And
Initial velocity.
Initial velocity is 0. So V0. It's actually velocity and speed are both 0. Yep. Equals 0. Okay. And then that last part tells us is more of the find part of this. It says it wants us to find T and V when what equals 8 feet per second squared. Okay, so acceleration I usually write as a vector that's a function of time. Did it give me a vector as a function of time? No, it said at a particular time, something is 8 feet per second squared. It's a scalar. No, it's still, this is a little tricky. What they're telling you is the magnitude of the acceleration. Okay, they're saying regardless of how much is in the normal direction, regardless of how much is in the tangential direction, the magnitude of the acceleration at the instant I'm asking you about is equal to 8 feet per second squared. Okay. Does that make sense? Do we have any questions about that? Because that's kind of tricky. Okay, I'll leave you there. Go ahead and make an attempt. Welcome, Jordan. Let me know if you have any questions. I can hear you, okay? You're stuck? Go ahead and partner up. Try to figure out where you're stuck. I'll take over in 4 minutes. 10:50.
I use one. So number two. And then I use that. Here, I don't. I just.
Is this V the vector? Where is this?
That's what I think. Which is this. I was looking at it. Yeah. Magnitude, that's what I was saying. That's, so I never would do.
So this is not what we want.
I think so.
No,
Yeah,
that doesn't, no, that does make sense.
That's an expression of the vector. But we do know, what do we know about how speed changes? Given in the law? All right, I'm gonna take over here. My very first question after writing my givens would have been something along the lines of how much of the A vector can I fill out with what's given? So I would have done something like this. I'd have said, all right, the way it sits now, I can write A is equal to 7 U hat T. It's asking me for speed, right? So I definitely don't have V, but I do have rho. Okay, so I'm missing one thing, and I don't know what the acceleration vector is at the time it's asking me about, but I do know the magnitude of that vector. So what I can do is I can take the magnitude of this expression as I have it and set it equal to 8, which was given to me in the problem. Okay, so the magnitude of acceleration is going to be the square root of each component squared. So 7 squared plus v squared over 300 quantity squared. Set that equal to 8. And now all that's missing is v. Okay, so I can solve this expression for v. Turns out v will give us 34.09-ish feet per second. Okay, so this is the speed at the instant that it's asking about. And now we still need to find t. So this might have been the trickier part of the problem, is how do we then find t? And the thing we needed to realize is that we're given dv dt. So if dv dt is constant and it's 7, I can then integrate this. So I can separate variables and have dv. Notice I don't have a vector bar here. This is just the speed, the rate of change of speed equals 7 dt. Integrate both sides. And be careful about my bounds. What am I interested in? I'm interested in how, well, I know 2 points in time. I know that velocity or speed starts out at what? 0. Yep, because that's given in the problem. V0 equals 0. At time equals 0. Okay, so I'm going to start out at time equals 0. And then I know that at some point in time, speed becomes what I just found, 34.09. And the whole point of doing this is that I need to find out what time that happens at. So t final is what I'm looking for. Okay, so if I go ahead and do this integration, I should get, I get v from 34.090 equals 7t 0 to t final. So this is 34.09 equals 7 t final. T final equals what? 4.87 seconds. That's it. Okay. How are we feeling about today's problems? Okay. Okay. One other kind of meta-analysis I want you to think about is that I was still giving you guys pointers on these problems. Okay. I was helping you set up the problem and do the first couple steps and interpret the problem statement. Recognize that on an exam, you have to do those things completely on your own. So those are skills that you still need to be developing outside of what we did here today. So yes, today was great work, very good practice, but you still need to be doing the homework and testing yourself on whether you can do these problems without any training wheels on. Okay. All right. Awesome. Thank you so much for joining. I definitely appreciate you all being here. And I will see you all in class tomorrow.